Okay, welcome back to the session. So it's my great pleasure to introduce Denis Talay from INRIA. So for 20 years, Denis Talay has been heading INRIA research team in stochastic modeling and stochastic numerical analysis, now TOSCA. And in parallel, he has been professor of École Polytechnique in Paris for 13 years. From 2006 to 2009, he was president of French Applied Mathematics Society, XMA, and he's now chairing the scientific committee. And he had and still having important editorial activities in the board of more than 12 first-rank journals in probability or numerical analysis. So please welcome Denis Talay.
Thank you very much for this introduction. Thank you very much to the scientific committee for the invitation. And thank you a lot to our Korean colleagues for the wonderful organization of this wonderful conference. So for them, I will try to say thank you in Korean. That's Gemsa Amnida. So, I will speak on some singular stochastic computational models, and what I'm interested in emphasizing here is how much we must make interact stochastic analysis, PDE analysis, in order to analyze these models and to develop and analyze numerical methods. So that's the outline of the talk. So after a brief introduction, I will give some reminders on smooth models. So that's parts 2 and 3. And then progressively I will attack more and more singular problems. So the models in parts 4 and 5 are, let's say, gently singular, and the models in parts 6 and 7 are really unpleasant. So, what I mean by stochastic computational model is a family of models which are being developed or were developed in the past in several fields: biology, ecology, fluid mechanics, geophysics. And in all the situations where these models may be useful, physical laws are not fully known or suffer from the curse of dimensionality. And they are so complex, the phenomena we are trying to study, that adding simply noise to deterministic models or randomizing parameters may not be enough. So I list here some examples where these models were developed: biology, in neuronal modeling, simulation of winds, waves, complex flows, geophysics, dynamics of populations, finance, and so forth. So, to summarize, I want to emphasize that the models I will consider are designed to simulate complex phenomena. They take into account parts of the physical laws which are underlying these phenomena, and they are designed to approximate deterministic macroscopic physical quantities. So, by nature, because the phenomena are complex, the stochastic computational models I'm interested in inherit singularities from the physical laws they are aimed to mimic. And because of that, their efficient and accurate simulation is questionable, and actually is still an open question in many aspects. So the aim of this lecture is to review some recent developments concerning the numerical approximation of this singular stochastic dynamics, and to illustrate novel issues in stochastic analysis, PDE analysis, and numerical analysis related to. So brief review on stochastic dynamics with smooth coefficients. So I limit myself in this talk to stochastic computational models written in the form of singular stochastic differential systems. There are plenty of other ones, especially in statistical mechanics, or in biology, which include branching processes, control processes, random processes on graphs, etc. I will focus on stochastic differential systems. So the basic object in the story is stochastic differential equations. That means this guy, so if sigma is equal to 0, we recognize an ordinary differential equation. When sigma is not 0, you have to take into account a stochastic integral and stochastic differential calculus. I will not use stochastic differential calculus in the slides. Of course, it's involved in all the proofs, but I will focus much more on the properties of the process X. So don't worry if you don't know so much in stochastic differential calculus. Hopefully you should not be lost. So, to the preceding stochastic differential equation with coefficients b and sigma, I associate sigma with the first script a, which is a function sigma sigma star. Second, the differential operator capital A, which is b times the gradient plus 1/2 a gk times the second derivative with respect to gk, the direction g in k. So that's an elliptic operator. And to introduce the fact that everywhere in the talk, in the proof, in the analysis, we need the link between the previous stochastic differential equation and PDEs, I'll immediately write down the parabolic PDE governed by the operator L. And by stochastic analysis techniques, one can prove that this function, the expectation of f, where f is a test function, applied to the solution of the stochastic differential equation, issued from x at time 0 and observed at time t. So this quantity, expectation of f of xt x, is unique solution, which may be classical or viscosity, to the parabolic PDE. And what I mean by stochastic analysis techniques, blah, 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 I mean that very often we can prove that this quantity actually is a solution. And second, if there is a solution which is smooth enough or is a viscosity solution, then this solution needs to be equal to this one. So actually, the stochastic representation provides existence and uniqueness results for the PDE. And if you look at the dual operator L star, the formal dual operator L star, it's easy to prove that the probability distribution of x at time t solve the Fokker-Planck equation du mu t over dt is equal to L star mu t. Okay. So now I would like to make you understand this story, even if you're not a probabilist, and without using stochastic calculus. So I use, in fact, x bar, which is a discretization of the stochastic differential equation, but you may forget the stochastic differential equation. Please just remind b and sigma, and suppose you're given a family of independent Gaussian variables with mean 0 and variance equal to t over n, where capital T is the time horizon of your problem. Okay? So then you construct this random sequence up to time capital T. So, first, the preceding theorem, which tells you that ut of x, which is the solution of your parabolic problem, is equal to the expectation of f of xt. Of course, you may approximate u by the expectation of f of x bar, at least you hope so. And then you use a Monte Carlo method, if possible, if you are able to simulate independent samples of these sequences x bar, which is easy. You have independent samples of Gaussian laws in your hand, and then using a Monte Carlo method, you approximate this expectation by this average. I have a timer. Okay. So what's the error in terms of the number of simulations? So you have the central limit theorem, which gives you asymptotic results on the normalized numerical error, but you have much more precise, because non-asymptotic results available in the literature. Namely, you can, if you divide by square root of n the distribution of this random variable, the error divided by square root of n is Gaussian, approximately Gaussian, and you may expand the distance between the distribution of ES and the Gaussian law. And in particular, you may get statistics, for example, the expectation of the absolute value for any capital N and any strict N which governs the time discretization is bounded from above by a constant which is uniform with respect to the time discretization over square root of n. And you have more precise results due to Lemaire and Menozzi to describe the probability that your statistical error due to the simulation of samples may get large values. Unfortunately, the probability that this statistical error gets large values is exponentially small. And the constants here are uniform with respect to strict n, which is the interest of the theorem due to Lemaire and Menozzi. Okay, now what about the discretization error? So what about the error due to the fact that instead of looking at the exact solution to the stochastic differential equation, I look at the process X bar I simulate on the computer. So in various contexts, this error, if the data of the problem are smooth enough, this error can be expanded with respect to 1 over n. So the story was, the beginning of the story was in the paper with Luciano Tubarro, and then many authors examine many situations. And the interest of that is that, of course, then you may use Romberg-Richardson extrapolation procedures, which means you run the Euler scheme with 2 or 3 different step sizes, you interpolate, and then you have high accuracy result without complexifying the scheme, which is a key point in the story, because the complex phenomena I'm interested in typically have a very, very large dimension. Okay. So just to make you understand by hands the story, compute the expectation of delta x. So delta x is b times t over n plus sigma times a Gaussian, which has mean 0. So the expectation is the expectation of b times t over n. And if you compute the second moment, is the expectation of sigma star at point x bar at time p, let's say, times t over n, because the variance of the Gaussian increments is t over n, plus a remaining term which is order 1 over n squared. Okay, and it's not difficult to be convinced that if I compute conditional expectation with respect to the past up to time t, we have exactly the same formula. So now, look at my error. So this is what I can compute with my computer, and this is the quantity, the solution of the parabolic PD. So f is u at time 0. So I express this quantity by means of a telescopic sum, this one. And now I simply merely compute a Taylor expansion of this quantity around this point. Okay? So the first term is just an expansion with respect to time, so it's minus du over dt, because it's capital T minus t. And then delta x times the gradient of u, but delta x leads you to b times t over n. So t over n times b times the gradient of u. It's at the beginning of n, capital A, the generator. And then you have 1 over 2 times delta x squared times the second derivative of u, and then because of that, you get t over n times 1/2 times the Hessian of u times. So you get time over n times Lu at this point. And now you use the PD, du over dt is equal to A of u. All the remaining terms of locally of this order, you sum up and you get an approximation. You get that the Euler scheme has an accuracy of order 1 over n. And this gives you a feeling, of course, also now substitute x to x bar. It explains you why expectation of xt should be equal to u t of x when n goes to 0. So of course there are many difficulties I've hidden. First of all, the existence of uniqueness of the solution of the parabolic PD and of the stochastic differential equation. The fact that I can compute differential derivatives of ut of x. I need accurate local estimates on derivatives, in particular to prove that everything is integrable in the story, and that I can bound the remaining terms, which are expressed in terms of derivatives of u, uniformly with respect to script n. And I need also to make n tend to infinity in order to get the stochastic representation exact ut of x is equal to the expectation of f of xt, and then when n goes to infinity appears the stochastic integral. I don't want to present more here. Okay, now a story a bit more complex, because now I'm going to look at particles which so the coefficients of the dynamics are no more script d and sigma, but they depend also on the motion of each particle depends on the empirical distribution of all the particles. Okay? May forget the formula is not, I mean it's important, but the important thing to remember is that the coefficients of the dynamics depends on the distribution, empirical distribution of the particles. So, due to seminal works by McLean and Snickman, when everything in the story is smooth enough, we can prove that the particle system propagates chaos in the sense that the empirical distribution of these particles converges to the probability law of a process, which is a bit more complex than the preceding one. The stochastic differential equations, without any surprise, involves the probability distribution of the solution we are looking for. So it's a nonlinear problem, and it leads to nonlinear PD. The nonlinear Fokker-Planck equation corresponding to this dynamics is governed by by the formal adjoint of this nonlinear elliptic operator, which depends on the solution nu probability distribution you're looking for depends. D over dt is equal to L star nu t, and L star depends on the solution you are looking for. Okay? So, how to approximate this kind of quantity? You apply the Euler scheme to each component, to each particles, and then you can simulate and you get an approximation of the empirical distribution of the particles. Well, so convergence rate, one example. Take the scalar conservation law, which is here, where pi is a smooth function, it's a C1, and interpret this, you may interpret this equation as the nonlinear Fokker-Planck equation before, but then you get interactions extremely singular between particles. I mean, they would be governed by Dirac measures. But you may also interpret this equation as the equation for the distribution function of nu t. And then the problem becomes a bit more regular. I mean, here is the motion of the particles. There is no more Dirac measure. There is only the Heaviside function. And then Miribossi and Benjamin Jourdain could prove that the global error due to the time discretization of the dynamics of the particles and the number of particles is c over script n plus c over square root of n, that is exactly the same accuracy as when the particles are independent, in spite of the fact that they interact through the interaction kernels. And the explanation of this phenomenon is that the particle system propagates chaos. So in that sense, finite size family of particles tend to be independent when capital N goes to infinity, and independent samples of the law of this process. So that's it's a hard result to get. Okay. Now, let's see what happens when the coefficients are not smooth. So I start with the case where sigma is continuous, but B is only supposed bounded and measurable. And I suppose that the elliptic operator L is strongly elliptic. So a very natural procedure consists in smoothing B by use a smoothing kernel, for example, a convolution kernel. So you define now a new stochastic differential equation, and then you discretize by using the Euler scheme as before. And under some hypothesis, very weak hypothesis on the test function f, but an hypothesis on the solution of the parabolic PDE whose f is initial condition. Then Arturo Coatsuliga, Antonio G, and Yasuda could prove that if these conditions are satisfied, then for some explicit kappa, the global error of the method is of this type, and again, kappa is explicited. In particular, their result is so precise that you may choose epsilon in such a way that for a given kappa, you realize this estimate. And in addition, you may prove that in some circumstances, that is, if your approximation B epsilon is smooth enough, then the discretization of X epsilon remains of order 1 over n. So there have plenty of variants of these estimates. I don't insist too much. Now, the second example where the singularity is not so nasty. I'm interested in, and I will understand later on, I'm interested in the relationship, what happens when the particles have singular behaviors at boundaries. And maybe the simplest situation is the following. In terms of PDE, we have a flux condition. Let's say at point 0, I start with the one-dimensional problem. Okay? The solution needs to be continuous everywhere, including 0, but the first derivative of u is discontinuous at 0. And A of x may be discontinuous. So we are no more in the case of Arturo, Antoine, and Yasuda. We are in the case where A is discontinuous, and if you expand this, then the drift, the coefficient B, becomes a Dirac measure. So it starts to be rather singular, but you have this nice divergence form structure, which plays a big role and which simplifies a bit the singularities, the problems due to the singularity. Okay, so now what becomes a stochastic representation? We have first the same dynamics as before, but I need to add a term, which is not so much complicated, in fact. It's a local time term. So it's a certain coefficients related to the discontinuity of sigma star times this process, and this process increases only when x, in that case, when x reaches 0. But anyway, it's difficult to approximate numerically because it's given by this limit, 1 over epsilon plus blah, blah, blah. So if you substitute this quantity to the dynamics here, you have the drift term b of x, which becomes sigma prime, good, but plus 1 over epsilon times blah, blah, blah. And as you know, if you discretize a system where we have 1 over epsilon, you instantaneously get enormously difficult numerical difficulties. So, so, first of all, as I told you, stochastic analysis techniques may provide you ways to exhibit solutions to the PDE, and that's an example. We could prove with Michael Martinez that the expectation of f of x, the preceding process with the local time involved, this expectation is actually the solution to the preceding PDE. There is only stochastic calculus in the term. And in addition, owing to this stochastic representation, we could get a lot of accurate estimates on the local estimates on the derivatives of u, including anywhere close to the singular point 0. And observe that here we have, that's very usual, 1 over square root of t, which is the upper bound for these derivatives. And you will understand in a few minutes why I insist to this point. And in some sense, this 1 square root of t reflects a part of the singularity of the problem. Okay, so how to construct a numerical algorithm? So to prove that the preceding system with a weighted local time has a solution, Le Gall years ago, and for more general SDEs of this type, introduce a transformation which in that case becomes very simple. And so it's a function. It's a function which is of that type, which is piecewise linear. You apply this function to the original process x, and then you get a new process y, which solves a new stochastic differential equation. And what is very nice is that this differential equation has no more local time involved. Okay? But the coefficients are discontinuous. Anyway, you can apply to your Euler scheme. You apply the invert map beta minus 1. You define a discretization of x. But you simulate Euler for y. You apply beta minus 1. So you can do it very easily. And the accuracy of the method is of this type. Unfortunately, the techniques I just summarized here are typically one-dimensional. So what about the same problem, but, excuse me, the K ingredient in the proof is the following, which it comes with a paper with Frédéric Bernardin, Mireille Bossy, and Denis Talay. It's a discrete time version of Krylov estimates for stochastic integrals. So the difference with Krylov works is that we deal with discrete time, and we have weights in the story, a function g here, which is of that type, or maybe 1 over capital T minus t, the power different from 1 over 2. And that comes from the fact that the derivatives of the function ut of x and intrinsically may behave like 1 over square root of capital T minus t, as we saw before. And anyway, the left hand side here is a kind of measures of the time spent by the process capital X in small a small ball around the singular point. Okay, so we have these estimates both for the exact process X and for the Euler discretizations, with constants here and order here, which do not depend on scripting. So I think these estimates are maybe useful in many other contexts. So now what about the multidimensional interface problem? So let's start with the Poisson-Boltzmann equation in molecular dynamics. So in the story we'll have two functions, kappa and epsilon, and these two functions are discontinuous, but constant inside the molecule, so they take the value 0 or epsilon int, and constant outside the molecule. So here is the equation, which looks like the 1D problem. So now we have at epsilon of x, which is discontinuous at the surface of the molecule. We have this linear term I did in the story, and the problem here is elliptic and no more parabolic anyway. And in addition, we have this very nice flux condition at the boundary, gamma, at the surface of the molecule. Okay? So what's the probabilistic interpretation of that? Again, we have classical stochastic function equation plus a local time term, but it was not so difficult, at least, it was not so easy, at least for us, to understand the structure of the local time term to add to the preceding term. And in fact, the point is that we needed to introduce a new process, an auxiliary process, which is the sign distance of the solution we are looking for to the boundary. And the local time term which is involved in the story is the local time of this auxiliary process. And again, the weight here is related to the discontinuity of A of x along the surface of the molecule. And we can prove that this guy here is the solution, the unique solution in a suitable space of the Poisson-Boltzmann equation. And why to do it? Because of course, mathematically it was a challenge, but also because it allowed us to justify an algorithm which is extremely efficient, a probabilistic algorithm, to solve the Poisson-Boltzmann equation due to Mascagni and Simonov, using the ideas of the Wacom spheres algorithm developed years ago by a Russian school, especially. So we could extend the story to the semi-linear Poisson-Boltzmann equation, which is more realistic, with Nicolas Champagnat and Nicolas Perrin. And then, very recently, with Sebastian Nikitschek-Soto, we could deal with the general multidimension case, which means that inside, so any dimension, not only 3, and inside, at each side, inside the domain and outside the domain, the coefficients may vary. Okay, now, I would like to speak about a much more nasty singular stochastic computational model. So it concerns the Reynolds decomposition of the velocity fields. As everybody knows in this room, you think of turbulent flows or complex flows as a deterministic part plus a fluctuating part. And I will focus on the model developed by Pope, which is an incredibly rich model, but incredibly difficult to study, as you will see. So, in this model, the Reynolds average part is supposed to be equal to a conditional expectation. The conditional expectation of a function of the velocity given the position of the particles. And the covariance of the velocity fields is supposed to satisfy this equality. So it's related to the well-known Reynolds average Navier-Stokes equation, except so this equation is not closed, so you have to define a closure, and the Pops propose a stochastic way to construct closures, to get closures. So in a simplified way, a simplified version of Pop's model is this way. The function epsilon, k, etc., or maybe discontinuous singulars and so forth. You have involved in the story conditional expectations. You have involved in the story Poisson equation governed by these conditional expectations. And you have specular boundary conditions at the boundary of the domain. So everything is difficult in this model. So with Mireille Bossy and Jean-François Jabir, we examined first a very simplified version, focusing on the effect of the conditional expectation, which appear to be a very singular way, a very singular version of the Makin interaction kernels. And we could prove that this system, in the whole space, propagates chaos exactly as for the smooth interaction kernel case. And this work is used deeply, results coming from the PDE literature due to Francesco and Pascucci on the transition density of versions of the preceding, of the Fokker-Planck equation for this system, excuse me. And again, we have this kind of singularity which appears in this. So and then Mireille and Jean-François developed the theory, and in particular, they solve the difficulties due to the specular boundary condition, and this is a very nice piece of work. And also, they could prove that the crucial no permeability boundary condition is true for the preceding system. And there, Mireille is getting theoretical estimates on the discretized version of this system. Now, I conclude with another system where the interaction becomes still more non-standard, and the motivation comes from neurosciences. So in these models, you have no interaction kernels, but when one particle reaches a threshold, then it impacts the positions of all the other particles. Okay? So what happens if ever one particle hits the threshold, then the weight of each part of all the position of all the other particles are increased by 1 over a, or alpha over a. Okay? So this is a very singular interaction way. And here the process M is the number of times the particle passes the threshold. So from a neurosciences point of view, that's the number of spikes of the neurons. Alpha is a given strength. The related Fokker-Planck equation is this one. Observe that there is a Dirac measure in the source term, and observe that there is this boundary condition which is nasty. And this PDE has been studied a lot by several authors recently, including in particular the very nice work by Carillo, Pertam, and their co-authors. And they prove in particular that the solution may blow up if alpha is too large. And for any alpha, there exists an initial condition to these Fokker-Planck equations such that the blow-up occurs at finite time. But now, if you develop a stochastic interpretation of the preceding Fokker-Planck equation, or if you develop the mean field limit of the stochastic particle system, what you could prove is that if alpha is not too large, And if the initial condition is deterministic and not close to zero, too much close to zero, then the process here is, the midfield limit is absolutely well defined. It doesn't blow up, and the corresponding Fokker-Planck equation doesn't blow up as well. So the numerical analysis is being developed by the same author, François Delarue, James Inglis, Silver and Denis Talay, Denis Talay. And I'm just finished a work with James Inglis on a variant of this above model, which is different by several ways. I mean, there is a stochastic integral here. The synaptic weights are not constants. But there is a smoothing part in the story which simplifies a bit the analysis, because the Fokker-Planck equation for any value of the parameter doesn't blow up. So it's, in the sense, it's more simple than the story developed by Bertin Carrillo from the PDE side and this author from the stochastic side. So to summarize what the main message I tried to explain, and again, it's a very, very narrow vision of what is being developed in the world, in the literature, on such singular models. What I try to emphasize is that in the story which involve continuous space and continuous time processes, the interaction between PDE analysis and the stochastic calculus is absolutely necessary. And even in recent works concerning stochastic kinetic models or particle systems related with coagulation and fragmentation of particles, coalescence. For models developed in biology, in particular branching processes and so forth, and for stochastic partial differential equations appearing in neurosciences in particular, again, to analyze the model and to analyze stochastic numerical methods, we absolutely need to play with all the analytical tools coming from the deterministic side and the stochastic science. And of course, I've not at all tackled very important questions such as the sensitivity of the results to the model uncertainties, which is a very important issue, because we are interested in only computational models for phenomena whose physical laws are not explicitly known, fully described. And also, I have not discussed the very important variance reduction techniques which need to be developed. And this is very important again, because typically, because of the singularities and the dimension of the physical phenomena we are interested in, the number of particles capital N typically is huge. It's 100 of millions, for example. So any gain to reduce the variance is very interesting. So thank you very much.
Okay, thank you for very interesting talks. Do we have time for questions? Okay.
I have two questions.
Hello, I have two quick questions. One is, how does the numerical method, the ones you've developed, interact with the geometry of the domain, which is kind of the theme of the previous talk? And secondly...
First,
yeah.
I'm afraid to forget the second question when answering to the first one. So that's so in the 1D case, you observe that I could get rid of this issue just by a change of variable. For the Poisson-Boltzmann equation, typically what without any surprise. You localize the boundary, and then you use a coordinate. You change the coordinates in order to transform the surface into an hyperplane. Okay. For the two last problems, that's a very critical issue. In particular, Neuroscience developed a lot of machinery to solve this question. I have no time to just, I mean, even to introduce the ideas between behind the algorithm, I will need several minutes. But that's a very, very crucial issue.
The second question was about the variance reduction. Like, how does, have you thought about, the statistical techniques like Rao blackwellization, basically using conditional densities? Like, so you take a numerical method and then improve on it by using conditional methods. So,
Yeah.
does that work?
But again, there is a huge work to do. I mean, so far, in the small number of numerical trials which have been made, one density kernel estimator has been used, but there are some other ones probably much more efficient. Yeah.
Thank you.
So we need statisticians to help us, obviously.
Any more questions or comments? If not, let us thank the speaker again. So we'll resume at 10 after 4 or 5, I forget.